Well, the title of my talk, as you can see, is slightly different from what initially envisioned. So I will give you an introduction about graphene and why do we need and we want to study also other 2D materials different from graphene. Okay, as just Anita has nicely introduced about graphene and how we can actually obtain graphene. Sorry. So if we start from graphite that we can find in any LEDs in pencils, for instance, that those images shows. Graphite is formed by these layers of carbon atoms. So these layers of carbon atoms, they have very strong interaction. So the individual carbon atoms are strongly interact one to another one, but the individual layers, they have very weak interaction. So we can actually separate these layers very easily through the process that we call exfoliation. And we can isolate graphene as a single individual sheets of carbon atoms arranged in hexagonal structures. And as you can see here, there is the image of one of the first graphene layers isolated onto a specific substrate. And we can actually see these graphene layers just using an optical microscope. Well, I will not go through in details all the properties of graphene that many of you perhaps are already aware of. But I would just like to recall for people who are new to graphene why we are so interested in graphene. So it's a thin and slow material. It is extremely strong mechanically, extremely flexible, so we can stretch it very well. It's optically transparent and can conduct electricity very efficiently, better than copper, and also can conduct heat very efficiently. And for instance, in this picturization, we can see how the mechanical properties of graphene sits compared to other known materials. So we can see that can be ductile as rubber, but at the same time can be very strong as a ceramics or a metal alloy. And so, however, we like very much graphene, but at the same time, graphene cannot serve any possible use. So we can also look at other two-dimensional materials that can have complementary properties of graphene. So first of all, we are so interested in two-dimensional materials because the properties of individual sheets, as graphene has demonstrated, can be very different from the properties of their bulk counterparts. So isolating individual atomically thin layer can enable new properties that are not found and proper of any other materials. At the same time, we can manipulate these two-dimensional layers as individual particles. So we can use the same processing techniques that we typically use for ceramics materials or for polymers and to these two-dimensional materials. So we have some of the tools of manufacturing, how we can actually process these 2D materials. And we can also try to assemble these 2D materials, try to create structure where the properties are not only dictated by the properties of the individual layers that we assemble together, but also by the properties of the structure itself. So the geometry of the three-dimensional structure that we are creating. So having a tool to exfoliate this material and assemble them in a specific order can give us a new tool to construct devices or what are called three-dimensional constructs with new properties. So along with graphene, we can see in this slide there are many others. Here are just a few examples of layer compounds. So layer materials where that presents a strong interaction in plane and weak interaction out of plane. So we can isolate like triatomic layers of molybdenum disulfide or oxide materials, or we can have also individually atomically thin layers like graphene formed by different atoms like boron and nitrogen. Or, for instance, we can have other 2D materials that are currently used and known as natural occurring minerals, such as mica. Also, molybdenum disulfide actually is a occurring natural mineral, although maybe less known than molybdenite. Okay, so all these 2D materials anyways needs to be isolated. As we know, the first example of how graphene has been isolated for a long time by physicists is via mechanical exfoliation. So just we take a Scotch tape, and if we have a natural crystals of graphite, we stick on the Scotch tape, and we start peeling off the Scotch tape layer by layer, so we can thin down these graphite crystals, and we can obtain smaller and smaller flakes up to the point that if we place the Scotch tape onto an appropriate substrate, like a solid substrate, like silicon oxide, we can obtain an individual layer of graphene. So this is an example of optical light microscopy image where we can see these different structure of graphite, few layers graphene, and we can recognize them from their different colors. So they interact differently with the light, so thicker material will have different colors from thinner materials. And however, Scotch tape method is not scalable as a method per se to try to achieve large-scale production of this material and to really use this material in devices. So ideally, what we want to have is this material in a suspension. For instance, we want to have these two-dimensional flakes, suspended in water. And from this suspension, we can actually manipulate these 2D materials in many different ways. So we can deposit them onto an appropriate substrate, or we can try to assemble them to form different three-dimensional constructs. And ideally, then, we want to try to scale up the synthesis which occurs in liquid phase and try to have a large-scale production of these materials. So in the last few years, well, many groups in the world and also ourselves, we have been working also on this slightly different version of graphene. So this is a hydrophilic version of graphene. So the possibility to have graphene dispersed in water actually is quite difficult because graphene is very hydrophobic. So, but if we attach opportunely functional groups to graphene, like in the form of hydroxylase group, we can make what is called chemically derived graphene, and this material becomes hydrophilic, so we can actually disperse this in water. And we can easily obtain this material from, just starting from bulk powders of graphite, and we process with different chemicals in order to oxidize these graphite powders. So we attach all these oxygen functionalities. Actually, this graphene oxide is somehow a very old material. It was initially seen in a transmission electron microscope in 1961 by this German scientist, Boehm. And so the interesting properties of this material that can be produced in large scale in liquid phase. So we can just obtain a suspension of these graphene layers in water. And then from here, we can manipulate these layers in the way we want. So we can, for instance, reassemble them to form atomically thin layers over large area. So those layers can be very uniform. So for instance, we can deposit them on plastics. So if we want to enable any application of plastic of these layers, it's possible, as we can see in this image, by a different methods, assembly methods, which are proper of other materials or inks, for instance. So they're really developed as a scale-up methods to deposit materials, nanoparticles, inks onto any substrate. And so what we can do, for instance, with these thin films, one of our interests, for instance, was to try to develop membranes based on graphene. So if we look at the assembly of these graphene layers in a mosaic-like structure, so we have one layer on top of another one, and here we have a picturization of what would be the side view of these membranes, of these thin films of graphene. And we can identify between one layer and the other one, there are possible paths for instance, liquid to go through. And if we control the length of this path and the distance between these layers, we can actually engineer a membrane. So we can use these thin films as selective membranes. Example, for instance, we use these membranes to isolate dyes from water. So here we see this suspension, color suspension, where we have different molecules, larger and smaller. And these are actually color suspension by dyes. And so if we see on the left-hand side, we have the liquids that we filtered through the graphene membranes. And on the right-hand side, we see the liquid which have been filtered through graphene. So we see that the liquid which has been filtered through the graphene membranes is actually transparent. So graphene can actually retain all these molecules very efficiently. And those membranes are very stable. So we can run those membranes for weeks, and they are perfectly stable. So we are all familiar about membranes for water purification, which are typically can be based on polymers or ceramics materials. So graphene membranes represent a new type of membranes, which have the same advantages of using polymers membranes, so they can be processed at low temperature, at low cost. But at the same time, they're very stable in air. So they share the same properties of ceramics membranes, being very stable, but at the same time be easy to process. And then, as I mentioned, there is another way that we can try to assemble these graphene layers as well as any other 2D material, so forming a three-dimensional network. So we see here on the right-hand side a microstructure of what is called graphene hydrogel, or we can call also graphene foams or sponges. So there are several methods now available which have been all inspired by the polymer chemistry to try to create this three-dimensional construct based on graphene. So we can see photographs, actually, how this construct look like. So they can be mechanically very strong. As we can see, they can sustain 100 grams of weight. And also can have a diverse range of properties. For instance, they can behave as self-healing materials. So if we cut them and then we put them together, they will be mechanically perfectly stable. So we can adjust any cut that we induce in this material. So at the microstructure level, all these different properties, we can understand why all these different properties are enabled, because the microstructure of this material is very different. So we can see we have all this random porosity, and we have this walls type of structure, which is formed by a few layers of graphene assembled together. And a major advantage of using graphene to make these three-dimensional constructs versus other polymers is, for instance, those constructs are electrically conductive. So while typically polymers constructs are not electrically conductive. And at the same time, they're mechanically much stronger than currently known constructs. So, well, there are a few different, let's say, weak bonding that we can exploit on the surface of graphene and graphene oxide to induce this assembling in 3 dimensions. And this different bonding can actually induce different microstructure. For instance, if we start from a suspension where we had these graphene oxide layers in water, and we add some oil inside, and we control the viscoelastic properties, we can even have a suspension so viscous that we can print it. And if we leave it dry, we can obtain a solid materials. So as we can see in this image, we just extruded graphene oxide suspension through a syringe. And on the right-hand side, we can see electron microscope images of how it looks like, this construct at the micro level. And on those lines, so we focus our attention trying to create different 3-dimensional networks with different microstructure to see how we can then tune the properties of the overall structure. So we can obtain structure which have a cellular microstructure, as we can see in this case, where the individual walls actually are formed by just 1 or 2 layers of graphene. Or we can obtain structure which are more what we call lamellar structure, so are more elongated. So here we have an example of, again, using electron microscope of the side view of the structure and the top view. So obviously these two different structures, lamellar versus cellular, we have also very different mechanical properties and also electrical properties. One example of the application of this 3-dimensional construct, for instance, is for oil absorption. So one of these constructs have overall viscoelastic properties that we can mechanically compress it, and then while releasing the mechanical compression, this material can retain exactly the same shape. And on top of that, the material is highly hydrophobic. So as we can see, the immersion of this material in an emulsion of water and oil will allow the preferential absorbance of the oil part of this suspension by the three-dimensional graphene construct. And we can, for instance, think about how to isolate and extract oil which is dispersed in an emulsion as a result, for instance, of oil spillage. And the particular characteristics of these sponges is that we can squeeze out the oil several times. We can reutilize these sponges several times. And their performance, so, which is measured by the grams of oils that these foams can absorb versus the grams of foams that we actually have, is very high. So we can absorb up to 200 grams of oil per gram of material. And this is quite competitive versus many other three-dimensional constructs which are currently available. And this particular ability to reutilize several times the same sponges is quite unique. As I mentioned, along with graphene, now we have a wide range of other 2D materials that are currently explored, and in particular for their optoelectronic properties. And amongst these several other compounds, which are layer compounds, we can think of isolate, single layer, individual layer from those compounds. There is this large family of metal dichalcogenides, so compounds of molybdenum, tungsten with sulfur and selenium. And their atomic structure is formed by this sandwich structure between one metal atoms and two chalcogen atoms in a sandwich-like structure. This is an individual layer. And in particular, they're very interesting because they can absorb light and emit light in the visible range. So we can think of using this material for various photovoltaics applications or for light-emitting devices. For instance, here we have an example of optical microscopy images of a few of those nanosheets of this material, or also platelets or flakes. And then we can see how different colors indicates the presence of different number of layers. And then we see in the right-hand side an image of the same flakes, but in this case we are imaging the light that those flakes are emitting. And we can notice that where we have one layer, we have stronger light emission, so the color is lighter, while we increased the number of layers up to 3 layers, essentially we don't have any light emission. This is because this interesting absorption and emission of light, in particular the emission of light, occurs at the single layer level. So if we isolate one of these single layers, they will have different properties from their bulk counterpart. So that's why we are looking in using these individual layers. And again, as per graphene, the same problems, how we can scale up the synthesis of this material to enable various different applications. So in this case, for instance, we need to use a slightly different chemistry to isolate these different layers, so we can start again from powders, bulk powders of these materials, which can be synthesized, or we can find also as a naturally occurring crystals. And then we need to elaborate a little bit more chemistry to try to separate this layer one from another one. But similar to graphene, we then at the end obtain a colloidal suspension of these two-dimensional, very thin flakes in water. And so this represents a great advantage then to try to deposit this material onto any possible substrate. For instance, we see here an example how we can create a mosaic-like structure, thin films onto glass. And then we can use these thin films where the single layer properties are preserved for various different applications. For instance, we have been exploring using this as electrode for water splitting, photoelectrochemical water splitting. And so on those lines, there are several other applications that these other 2D materials can enable, which are essentially complementary to graphene, given the fact that this electronic band structure on this material is slightly different from graphene. So they have these strong light-matter interactions. So on the same line of graphene, so these two-dimensional materials can be easily isolated from their bulk counterpart. they can be reassembled in a two-dimensional fashion or three-dimensional structure. We haven't yet seen an example of how we can assemble these 2D flakes in a three-dimensional fashion like we have seen for graphene, but it's one of the areas where scientists are actually devoting a lot of interest and efforts in the recent years. So going towards the conclusion of my talk, so we have seen, besides graphene, we have many other two-dimensional materials, in particular sulfur and selenium-based materials, which present a strong light-matter interaction, and they can be used possibly in many different light harvesting application or energy storage also. And at the same time, we have seen how we can try to produce graphene in large scale, and how we can actually generate new structure made up of graphene that so far were properly made with polymers, but using graphene can actually enable different different function and different application of these three-dimensional structures. And well, I would like to acknowledge all the people who contributed to this work, my group at Imperial College and our collaborators at Imperial College and elsewhere, and obviously the Royal Society. Thank you very much for your attention.
Go ahead.
Okay, so the question I've got is, how do you think Geim and Novoselov got the idea of looking at the rubbish rather than the really nice carbon material in the first place? So what made them look at the sellotape?
Who is that question addressed to? Sorry.
Maybe both of you?
Both of you. Both of you.
Both of you. So Cecilia first.
Was also a way of preparing like crystals for different spectroscopy or microscopy measurements. Well, I guess I had the intuition that something more interesting was on that side of the tape. If you have something to add.
Yeah, from my understanding, one of the motivations for that whole line of work was to try to make a transistor out of metal, which is something that we're told never to do. And it was a graphite that attracted the attention of that team. And I believe it is recorded somewhere in Geim's Review of Modern Physics article about who it was in the laboratory that came up with the idea of actually looking at the Scotch tape. And it was not directly, I think, Andre and Kostya alone. There was a third person, but I don't recall who it was. They're probably the best people to ask this question.
Yes, go ahead.
My question was really just how far would this box go? My question was motivated by Thomas's talk, but it's probably applicable to you all. I'm not in this field at all, so it might be a stupid question. Thomas, you talked about layering layers of graphene and materials. So my question is, when does a 2D material become a 3D material if you're layering something?
That is a fantastic question. And that's actually a question that reviewers of articles sometimes ask. So there's several notions of two-dimensionality here. One is the two-dimensionality from the perspective of being able to cleave a crystal apart into an atomic layer. And so that is asking about what is the anisotropy and the strength of the bonding between atoms in plane and out of plane. And so that can be quantified. It's difficult to make those quantitative measurements, but they can be quantified. And so that tells us something about the two-dimensionality from the perspective of chemical bonding. But in terms of electronic properties, it is possible to coax electrons to behave as if they are two-dimensional in a bulk semiconductor. So in all your cellular telephones, you are using technology that in fact relies on this very fact. So the transistors that are amplifying the signal that is picked up by your cell phone antenna, that first amplifier with that first transistor must be very low noise. And it turns out that forcing your electrons to behave as two-dimensional electrons in a three-dimensional bulk semiconductor is the key to make that happen. And the way to think about it perhaps is that what's needed is you need to confine your electrons in a quantum mechanical state that suppresses any motion in, let's say, the vertical direction. And so this is akin to taking a guitar string and forcing the guitar string to only play one note because it's so taut that you can't excite any other note than the lowest note. So that just means that you have to squeeze the electrons into a small space, but it doesn't have to be a single layer of atoms. You can still have a finite thickness of material and force your electrons to sit as if they are two-dimensional.
Just going to put the laptop down. Hang on.
Thank you. My question. So my question was probably aimed towards Thomas as well. Actually, although maybe either of you would want to jump in on this, we've kind of become accustomed in our electronics that they're not easy to peel apart in terms of in computer chips and things like this. Obviously, assembling these really interesting stacks of materials, we do it at room temperature and this kind of stuff. If they're easy to put together, are they easy to fall apart? And is that an issue in electronics?
You mean, can we shake our 2D layers off each other?
Yeah,
That sounds
we
like
often run chips at high temperature, for instance. So could they just fall apart?
Oh, things always fall apart. If you ask the graduate students in the lab, there are very many different mechanisms for failure that we still have to understand. So even how you put the metal contact onto a two-dimensional material, it's not trivial for a very interesting reason, which in retrospect is quite obvious. And it goes something as following, that if you have a two-dimensional material, then the bonding is very strong in plane, and you have very weak out-of-plane bonding. So that means when you want to put a third material on top, like a metal electrode, to have efficient injection of an electrical current, you have to find a way to attach something to this 2D material that doesn't really want to bond strongly to anything atop it. And that means that there are better ways for the fabrication to go than other ways. In practice, though, it's the behavior of materials on that scale. The forces are so enormous that in practice it's not really a problem unless you are thinking about macroscopic objects. So it's something that we don't really see that particular problem yet, but who knows? Who knows? I mean, it has important practical implications for the perspective. If you want to make a switch, for example, that operates on the basis of making an electrical contact on the basis of mechanical contact, the sticking forces between the two surfaces and how many times you can actuate that contact and breaking of contact is something that's not yet well understood, but it will most certainly need to be, because if you think about the number of times your transistor will switch in a chip, it's billions upon billions of times, so you really need to make sure you understand that. So it's definitely an open question, I would say.
Actually, I have another question for Cecilia. It was obviously these layered structures were really interesting, and you showed these really cool 3D systems. Is there any feasibility of combining these two, of making three-dimensional structures of layered materials?
Yes, well, one of the ideas is also to combine this two-dimensional material with graphene, making a three-dimensional construct. And that would expand the function that this three-dimensional construct can have, also considering the catalytic properties of these 2D materials and their strong light-matter interactions, which are limited in graphene. Yeah.
Actually, I have a question as well, if you don't mind. You mentioned quickly in your talk that you talked about 0D, 1D, 2D, 3D. I mean, people have done quantum dots for a long time, 0D materials. 3D materials, of course, have been known for a long time. 1D materials with nanowires, there's been a lot of work. You didn't get too much into what's so special, in your opinion, about 2D compared, for example, to 1D, 0D. You mentioned that 2D devices, but in the end, you could also have 1D devices if you could stretch a graphene ribbon into, thin enough that basically it becomes a wire, a graphene wire. Or a carbon nanotube basically is a 1D material. So what's so special about 2D? Is it because it's easier for manufacturing integration, or what do you see so special about that? Maybe Thomas first and Cecilia after.
Right. So there are many aspects to this question. So first of all, I should say that there has also been a lot of work on two-dimensional systems, in the sense, not that the atoms have a two-dimensional nature to them, but that as I mentioned, there are ways to coax electrons to sit in a two-dimensional state in a bulk structure. So this is like the physics of quantum wells that have been studied for a very long time and have brought about a lot of very interesting new physics to us, especially under the application of a magnetic field, where you can, in very clean systems, study what happens when the dominant physics is driven by the way electrons interact with each other. From the perspective of electronics, there's a few other things. So obviously a planar technology is very beneficial. It was some time after the first transistors were made that electronics really took off, and one of those enabling discoveries was that you need to be able to make things in a planar fashion from the manufacturing perspective, because the entire semiconductor industry is based essentially on planar technology. So that's one aspect. Another one that I didn't really mention is about what is the optimum transistor. And you really want to have a very short transistor and also very wide. And the way to think about it is like from a perspective of a valve. You don't want your valve to be very long, but you do want it to be very wide so that it can carry a lot of current, whether it's an electrical or water current. You want a large current carrying capacity, but you also want it to be very short so that there isn't too much loss of pressure or loss of voltage, however you want to think about water or electricity. So all of that is favorable for two-dimensional materials. The 1D structure is very interesting, but it's not necessarily optimal for transistors. There's one other important distinction to note, and that's that in 1D, you don't have the freedom to wrap one particle around another. But in 2 dimensions, you do have that dimensional freedom. So it says that 2D is inherently different than 1D. And I'm not going to say that 2D is better than 1D, but it's just you have a different set of dynamics that is present that means that you can see different physics. And that's what some of us choose to be 2-dimensional people, and some of us choose to be 1-dimensional.
Yeah, so you've both clearly stated that this is an awesome material and that this is going to revolutionize our world. And then I wonder, even though you said, Cecilia, that this might be good also in environmental applications where it can soak up oil and these kind of things, is there any more in general, any ideas about what this material that is so strong, that lasts forever, what it does is in our environment? And if we are going to bulk produce it, is it going to be a problem or not?
Well, there are several studies on also in terms of toxicity, etc., considered for nanomaterials. So it all depends also in how they are embedded and what they are embedded, those materials. So, and at the moment, like graphene can really enable several different new applications of composites based on polymers. So, and the strong emphasis is also making those materials long-lasting. So while polymers at some point degrades, and then you have somehow to get rid of those polymers, graphene-based material potentially they can last much longer, so they can be used for long last of time. So we would consider in that way graphene-based material like material that we never really get rid of. So that could be a possible advantage. But obviously the field is still at the early stages, so it's difficult to really envision the first real application and for how long those materials can actually sustain. Yeah.
Quick question. Are these transparent? I'm kind of curious if I'm going to see all sorts of see-through computing down the line because of this.
That's very interesting. The transparency of the single layer of atoms depends, of course, on which atoms you choose. But let's take graphene as an example. One of the very curious properties of a single layer of graphene is that it is, let's say, 97.7% transparent. And that number is basically 100% minus 2.3%. I think I can do the math right, I hope. And that 2.3% is a very important number. It's pi times something we call the fine structure constant, which is a kind of important physical constant that denotes the strength of electrons, electron coupling to photons. And it is indeed the case that a lot of the interest in graphene and producing large sheets of graphene is driven by the interest to produce flexible and transparent touchscreens. So a large number of handset producers are looking at graphene as a replacement for the existing conductive electrodes such as indium tin oxide. But this remains a very large challenge to displace indium tin oxide because it is so cheap. And so economics is now a very big factor in determining whether graphene will ever replace existing transparent conductive electrodes. But that's something that has not escaped the attention of a lot of people that drives interest. And there's other applications perhaps in photovoltaics and so forth, but it's an active area of research.
Yeah, I would say that one of the main interests actually is also in these materials the fact that they are transparent. So also if we think of assembly up to 10 layers or more of this material, still this assembly will be transparent, so you can see it through. So, and devices to make effective devices of these materials, possibly up to 30, 40 layers will be enough, and they will be still transparent. So it's one of also the main plus of these materials. Yeah.
Pass it down the line. Pass it down the line. Okay. I think you touched on this a little bit with you mentioned about nanoparticles, right? Are there health issues with the graphene materials? Per se, just so with the nanoparticles, the concern is people can make these and then they get in the atmosphere and then they're inhaled, right, and stuck in your lungs. Are there similar health issues with the 2D materials?
Well, 2D materials can be actually much larger in terms of one dimension, can be up to millimeters or meters even. So in that case would be just adhering a specific substrate. Obviously, if we reduce both sides of these 2D materials, we make those close to 1D material, then there will be, there are studies actually on possible toxicity related mainly to the dimensionality as any other low-dimensional material. So yeah, would be, if there is any concern, it's mainly for those graphene or 2D materials which are manufactured very small. So they are comparable to other nanomaterials. And the main issue is the dimension, not much the chemistry that they contain, but it's their dimensions also.
Okay. And just to do with the cost, have people done life cycle analysis to look at the cost? Because obviously you need very pure materials, correct? And so the cost to make those is quite high, but if they last a long time, then that offsets that cost. Have people looked at the economics of that?
Yes, people are strongly looking into the economics, especially for the liquid phase produced materials. So how we can decrease the cost to make it actually effective. So this is also one of the reasons that can dictate some applications versus other applications. So the cost involved in making those materials, like using high temperature in a furnace, like the chemical vapor deposition methods involve much higher cost than making those materials in liquid phase, for instance. So those are all pros and cons that have to be taken into account then to decide what are the advantages of using those materials for novel application related to the cost of making those. Yeah.
Very nice talks. Let me ask you a provocative question here. So when would you think graphene will go out of fashion? Why?
Well, sometimes I guess also the other 2D materials now can be considered somehow more fascinating than graphene itself. So, well, it's not out of fashion, of course, but there are also these other two materials that sometimes attracts more attention than graphene itself now. I don't know if you want to add something.
Yeah, I'm weighing my words carefully. There have been some people who have said graphene is dead, but I think there's just the way that graphene itself started was very much out of the mainstream in some way, and so I think there may be a reduction in emphasis on graphene itself, but I would be hard-pressed to believe that there are still not more surprises that lie ahead. It's very difficult to predict the future with any accuracy, so who knows? I mean, now I would say that there's much more interest in all variety of 2D materials, and to give you an example of perhaps of how graphene still plays a very important role in electronics, the way that electrons move in one layer is affected by what is the environment around it. Because your electrons are essentially on a surface, they're incredibly sensitive to everything going on around them. And so graphene is great because it's kind of like a two-dimensional metal. And so maybe in some cases, and it's already seen in experiments, that if you put a metal layer next to your semiconductor layer, the electrons in that semiconducting layer are somehow protected from the environment by the graphene, and you get improved electronic behavior. So there's still results like this coming out where graphene still has some very nice uses and surprises for us, and I think it's just limited by our creativity. That's what I would say. But there's certainly some people that will say it's out of fashion, but that's fine.
All right. If I may, just a comment, in the microelectronics industry, people have been saying that silicon is dead since the mid-70s, roughly.
Yeah.
That's another question for Thomas. You mentioned indium tin oxide and its widespread availability. In terms of sustainability, is there enough indium in the world to bypass the potential usefulness of carbon-based electronics? Any comment on?
Definitely, that's something that's actively debated, and presently, although indium prices have gone noticeably higher, it's manufacturing cost that also drives a lot of this. That is to say, it's not just the materials, but all the infrastructure that goes around the process. And presently, the price points for indium tin oxide is much more appealing than graphene. But that's not necessarily to say that it will always be that way, but at the present time, that is the situation.
Thank you. Oh, I think I just delivered it to you.
Thanks. Yeah, I wanted to ask about the the electronics and the efficiency. You gave the discrepancy between the Landauer limit and today's electronics. So what is your opinion realistically with, let's say, those advanced electronics? How much closer can we get to this these Landauer limits? Because also you seem to indicate that one of the problems is actually the wiring between the transistors, and that would have probably stayed the same, right? That challenge. So yeah, I'd be interested in your comment.
Sure. So this problem is known for a long time, and there are a number of solutions that are floated out there, and this is a very active area of research now to try to figure out what can be done to improve energy efficiency to get closer to this thermodynamic limit, because we're so far away. There's so much room, and it's not an easy problem. So there have been some proposals to use light instead of wiring. So you imagine like a little miniature waveguide for light to connect electronics on one side of the chip to another side. And that brings in a lot of complexity about the efficiency of the light generation, the light transport, and then the transduction of light back into electricity. And it's something that drives a lot of nanophotonics research, for example. In terms of staying in the electronic domain, the idea is the following, that if you could somehow reduce the voltage at which your transistor operates, then you would be able to reduce the voltage that you are charging up the wires and discharging. And the amount of energy that's consumed goes as voltage squared. So right now we're operating at 1 volt, and that 1 volt is determined by the transistor. Now, if you could design a transistor that operated at half the voltage, you would then be consuming about 25% of the power that you were before. The challenge is that you want to make a transistor that operates with lower voltage, but the amount of current change that you can get out of a transistor per unit voltage is definitely limited by the physics of the transistor that you are using. And so there's also a thermodynamic limit there, and essentially we're very close to that limit for the way that transistors are currently designed. And the way that they're currently designed is that you have a potential barrier, and you put the barrier up to block electrons, and then you put the barrier down, and electrons can go through. Proposals to change this into another technology would be, for example, that you put a barrier up, and that barrier is always up. And it's just that you make the barrier either very thin or very long, and you rely on the quantum mechanical tunneling of electrons through that barrier. And it turns out then that you can, in principle, have much more current change per unit voltage change, and so that would allow you to reduce the amount of voltage that you use. But there are a lot of problems to overcome still with those kinds of ideas, but it's very much an active area of research.
And that will be done with those 2D materials, is that the
yeah,
idea?
there are already studies on trying to use these two-dimensional materials to control the tunneling, the quantum mechanical tunneling. And the advantage of the 2D material here is that they are so thin that it's very easy to control the profile of that potential barrier, more so than with a thicker lump of material.
I was just wondering, so you've already sort of started to get to this a couple of times, but what level of convergence is there between the quantum computing world and the 2D electronics world, if any?
There's definitely some interest, but I would say right now there's a tangential relationship between the two, in the sense that it's not quantum information that's driving progress in 2D materials, and neither is progress in 2D materials driving quantum information, although there is work to etch out little patterns in your graphene, for example, to capture one electron and to manipulate the spin of that electron to create a qubit for quantum information. But there's still very many material challenges there, and it's not, I would say, the mainstream. The mainstream is not to have an intersection between the two. It's tangential, I would say. Oh.
Thank you. Excellent talks. I have just a question on when you do fabrication of these 2D materials, do you get into the green chemistry principles, or do you go through the conventional chemistry and physics? It's both for both of you to answer.
Well, obviously we do try the green chemistry route first, and well, and then use conventional chemicals whenever it's needed. But eventually, we try to make all the processing. Once we learn how to make the processing with conventional chemicals, then we can also see for more green chemistry routes. For instance, yeah, there is quite an emphasis now on ionic liquids, using ionic liquids for exfoliation of these 2D material rather than organic solvents. And so obviously it's a path that is pursued by scientists. Yeah.
Okay, thank you. And the next question I have is, beyond electronics, do these 2D materials have applications in the health sector? Or they might have potential applications?
In the health sector. Yeah, well, there is quite an interest in using those materials for instance, drug delivery or bioimaging or various differentiated areas of interest in biology or even in bioelectronics. So to make devices to be embedded or to be just as a tattoo, which can be attached to our skin for monitoring body function. So yeah, there is a wide range of possible application of these 2D materials for devices related to biomonitoring of functions. Yeah.
Okay, thank you. So.
Maybe one question, Cecilia. You showed those sponges for oil. What advantage there? It was not clear to me what advantage graphene has over other spongy materials there. I mean, how does it behave differently?
So graphene is mechanically very strong, much stronger than any other polymers, but at the same time it's flexible. So ceramics material are not flexible as graphene. So graphene presents the advantages of ceramics as well as polymers. In addition to this, it's also conductive. So we can make sponges which are mechanically much stronger than polymer-based sponges. We can also sponges made based on ceramics materials, so what are called highly porous materials, but it will be very rigid. So they will not have the flexibility or the elastic plastic properties of graphene-based sponges. And in addition to that, either ceramics-based sponges or polymers-based sponges are not generally conductive. So those sponges made up of graphene can really have three different properties, which encompasses the property of ceramics, polymers, with the addition of electrical conductivity. So.
And what about the matrices loaded with carbon nanotubes, for example? That could be another way to do something like that, or is it?
Yeah, there have been research previously also in trying to make those three-dimensional structuring with carbon nanotubes. Graphene, in that sense, is also, we have to consider the cost of making those materials, and graphene with these two-dimensional layers, which can be as large as micrometers, they can induce they can make much stronger structures, much more solid than, for instance, carbon nanotube-based three-dimensional structuring. So there is an advantage of having this two-dimensional geometry, which enables stronger van der Waals forces to be recreated, stacking together just a few graphene layers. If you stack together too many graphene layers, we go back to graphite, and we have a very rigid and a brittle material at the same time. But having just a few layers of graphene enables having stronger van der Waals forces to keep the structure together, but at the same time maintaining the flexibility.
Actually, I have another question. I was wondering, we talked a little bit, Thomas, before the talk, so you know the punch. But one question I'm really wondering is, for you in the community, how did the 2010 Nobel Prize change the field, change the community, change the momentum in the research? What kind of change did you see in your community after 2010?
Sure. So one very noticeable phase transition, I would say, was that, and speaking very frankly, was the curiosity-driven nature of the research was somewhat overtaken by the influx of funding through a lot of graphene centers and so forth, with an emphasis on technology deliverables. So the expectation was raised that, oh, in 5 years we need to have graphene transistors replace silicon. And these kinds of things, I think, are quite destructive in the sense that they do sometimes give a false sense of the timeline required to really work out all the details to produce something that really works. On the other hand, there was also much more visibility for the work, which there's these two aspects. So it was great to see the excitement, and you could have undergraduate students who know about graphene because it's all over the press. But at the same time, funding administrators sometimes then believe that, oh, when will I be able to have my graphene computer? I don't know. So those were the two things that struck me the most, I would say.
Cecilia, what about you?
Well, I guess actually it was obviously in terms of, as Thomas was mentioning, as this event has been heavily covered by the press, increased very much the awareness, consciousness about discovery of new materials for new technologies. So I can see also more and more undergraduate students who knows already what is graphene, what are the properties of graphene under two-dimensional material. So I think has very much spread much more consciousness of material science also from material science point of view. So I think definitely the impact has been enormous, and all of us are benefiting out of that.
Okay.
I have a question for Cecilia. I was really impressed by this picture of the syringe squeezing out a line of graphene onto the surface. Can you say something about what would be required to get a 3D printed graphene structure? And if so, what kind of properties would this have that you wouldn't be able to get with other materials?
Yeah, indeed, actually, recently 3D structuring of graphene has been demonstrated with a 3D printer. And so the key point is how we assemble together these sheets in the suspension. So what is the concentration, how we control the chemistry of this suspension. And often we need also to add a few other molecules which helps linking one layers to the other one a little bit more strongly, but not too strongly. And yes, again, the mechanical properties are really different. So depending on how these flakes are assembled, they can be very strong and rigid, or can be very elastic or plastic. So, and depending on those properties, they can be used for different applications. So we can think of making batteries, electrodes, or capacitors, electrode based on graphene, because we can carefully control the shape of those electrodes up to the micron level, as well as we can make more large devices for bioelectronics applications. So then the range of application can be very much diversified once we can identify reproducible ways and a systematic way of dictate these different mechanical properties in the 3D structuring.
Thank you.
I guess I'm curious about the hydrogel morphologies that you were showing. And I'm curious whether or not magnetic fields can affect the hydrogel morphology internally.
Yes, well, possibly if we can also incorporate magnetic particles, or so we can also control the, let's say, the structuring with an external magnetic field. We need to induce some, so by assembling these 2D materials, or graphene in particular, with nanomaterials which have magnetic properties, then we can possibly control with an external magnetic field. Is that on the line of, I guess, what you were asking? Or
Yeah, I guess I just didn't know if the material itself was influenceable by magnetic fields or not, and whether or not you could use that as a dominant factor in trying to arrange the internal morphology of the material as it sort of forms into a hydrogel like you were showing.
Making like adding to graphene other materials, then we can actually perhaps have some we can try to control possibly this three-dimensional structuring with an external magnetic field. Otherwise, the structure per se is not really controllable by a magnetic field. Yeah.